We're going to continue with the second video of examples and problems for chapter 3. Example 311, right here they're asking what is the voltage source if we have a current of 10 milliamps and a resistance of 3.3 kilo ohms. We use the Ohm's law, solve for voltage to find what is the voltage needed for these two quantities to be met. So we use them and we end up with 33 volts. Now they're asking, what happens to the voltage if the current gets to 5 milliamp? So what should happen? The current was 10 milliamps before, now it's 5 milliamps. So the voltage is expected to half. So from 33 volts, we can just divide it by the factor that the current was reduced by, and that should be our answer, 16.5 volts. We can prove that using Ohm's law, where we have the new value for the current and the resistor stays constant. So we just multiply it out, and guess what? We get the same answer. So we could use that. We don't need to go through all the hazard of solving every time. We can use that relationship. In 3.12, this is interesting because we are so used to seeing a voltage source here. Now we have a current source. Current sources can be used. So it's usually customary that we use a voltage source. But in this case, they are saying that there is a current source and they're giving us the direction of the current source. And they're giving us the value and they're asking for the voltage. So again, we use the Ohm's law to solve for it, and we find out that we get 4.86 volts. Now this says, what happens to the voltage if the current gets reduced to 40 microamps? So it goes from 180 microamps to 40 microamps. So we have the old current to be 180. The new current be reduced to 40, so we can find how many times or what is the factor by which it was, for which it was reduced, and we find that it's 4.5 times. So now we have the original voltage calculated for the original current, but now we know that it's being reduced 4.5 times. So we can get this original voltage divided by the reduction factor, we get the 1.8 volts. So if we reduce the current from 180 to 40, we get a voltage of 1.08 volts. We can prove this by using the Ohm's law formula with the new current. The resistor stays the same, the current changes, so we calculate it to be 1.08 volts, which is the same as just using the reducing factor. Let's move on to example 3.15. They're saying that in 3.15, let me read that. It says, an amount of energy equal to 100 joules is used in 5 seconds. What is the power in watts? So here by definition, we know that power is the rate at which energy is consumed. So energy or work divided by time. They're telling us what is the energy, 100 joules, and the time is 5 seconds. So our power is 20 watts. But what happens if the energy is consumed faster? What happens if T, instead of being 5 seconds, it is 30 seconds? So what happens to power? Power has to be increased or decreased. It just makes sense that it has to decrease because time is at the denominator. So if the time increases, the power value should decrease. So if the energy is kept the same, we have 100 divided by 30, we get 3.33 watts compared to 20 watts. But what does this mean? This means that if you have a set amount, a finite amount of energy, and if you consume that energy fast, then you're gonna run out of that energy, since we know that power is a the rate at what energy is used. So, and this is very important to understand this, because we know that we are moving into electric cars. We see that they tell us, oh, buy the Tesla, it gives us 300 miles range. But if you read clearly in there, it says if you drive at a specific constant speed. And here in LA, maybe now that we're having this pandemic, we can drive at a specific rate with not being stuck in traffic. But if you drive too fast, your range goes down exponentially. If you don't drive properly, meaning by being a careful driver, your range of miles of that battery goes down. So this is why this is important to understand what is happening here. In problem 316, we are going to express the following power using appropriate metric prefixes. So we are going to go from 0.045 watts into watts. Why milliwatt? It's milliwatt because we stop when we find the first non-zero value, that it is a multiple of 3. What does that mean? That means that if I move this decimal point a multiple of 3 and I find a non-zero value, then that's where I stop. So let's see. I have 0.045. So I go to here is 1 time, to here is 2 times, to here is 3 times. That's how I know that I should go to the milliwatt. That is the closest next value that I can use the prefix. Yes, somebody can tell me why I don't use the microwatts. I will still use a prefix, but in order for you to write this quantity in microwatts would violate the fact that you can only have 3 digits to the left of the decimal point. That's why that is incorrect. So let's do that. That's how I find the milliwatts. So I said 0.045, 1 watt. So I can get rid of the watts. It has 1000 milliwatts. So I get 45 milliwatts. I do the same thing. Now I have 0.0000112 watts. 2 watts. So I have to count how many times I have to move the decimal point to the first non-zero value. So let's see. This is 1 time, this is 2 times, this is 3 times, this is 4 times, this is 5 times. I cannot stop here because 5 is not a multiple of 6. I have to continue to here because 6 is a multiple of 3. So now I know that I have to go to the microwatts. So I said 1 watt. 1 watt is equivalent to 1000 milliwatts. 1 milliwatt is equivalent to 1000 microwatts. So I get 12 times 10 to the negative 6 watts, which is equivalent to 12 microwatts. We need multiples of 3 for engineering notation, which is what we have for metric prefixes. All these micro, milli, kilo, mega, giga are engineering metric prefixes, multiples of 3. Very important. Then we have 3500 watts. We need to write it with the prefix, so we count 1, 2, 3. So we have to go to the kilo. So we go 1 watt has 1000. 1000 watt has 1 kilowatt, so we get 3.5 kilowatts. Now we are going to express these quantities not using metric prefixes. So I have 1 milliwatt, so it gets replaced by its equivalent. I have a 1800 microwatts gets replaced by its equivalent. We have 3 megawatts. It gets replaced by its equivalent. The kilo gets replaced by its equivalent. So that's how I write it. I can write it out using the zeros. Not necessarily unless it's specified. 37, it says determine the number of kilowatt hours for each of the following energy consumptions. So we have 1400 watts for 1 hour. So how many kilowatt hour I'm going to use? The first step, I have to take the 1400 watt into kilowatt, and by doing that I use this conversion factor, knowing that 1 kilowatt has 1000 watts, so I get 1.4 kilowatt. I multiply it by the time, which is 1, so I get 1.4 kilowatt hour. I do the same thing here, 2500 watts used for 2 hours. I take the 2500 watts into kilowatts, which is 2.5 kilowatts. Multiply it by the time, I get 5 kilowatt hour. And then number, that's it. Let's stop right here.